Okay, so with inverse matrices, the formula for a 2 by 2 inverse matrices, or matrix, sorry, is the same as 1 over jeez, 1 over the determinant, and then you multiply that by A and D switched, and then the negatives of B and C. If at any point the determinant equals 0, that means there is not an inverse for that matrix. Also, the thing behind inverse matrices, before I start giving an example, is that A times, or the matrix times the inverse matrix equals the identity. Okay, so remember with identity, with the previous video, it equals this. All right, now the proof behind it, if you were to apply it to regular numbers, is that, let's say you have 8, the inverse of 8, or 8 to the negative 1, this is the same as 1 over 8. So if I multiply these two numbers together, it gives me 8 over 8, which equals 1. And remember in the previous video, the identity matrix is the same as 1. So that's the concept behind all of this. So basically what you're finding with this formula is what times the matrix times what equals the identity matrix. So the first matrix times what equals the identity. Now, unfortunately, we can't divide matrices. So we can't divide the identity with the first matrix to get that inverse matrix, unfortunately. So we have to do that formula. But there's also another method. Let me go ahead and do this example. An example doing this formula, and then I'll show you the other way. Okay, so let's say I want to find the inverse of this matrix, right? So we're looking for the inverse. I'm going to do the determinant. So the determinant for a 2 by 2 is the same as A times D minus B times C, which we're going to talk about more in the next video. So A times D is 3 times 6, which is 18, minus B times C, which is 4 times 5, which is 20. And then we're going to multiply that by the original matrix, but like in a different order, kind of. So D is going to end up moving to where A is, and then A is going to end up being where D was. And then B and C stay in the same position, they just become negative. Okay, so 1 over 18 minus 20 is the same as 1 over negative 2 times 6, negative 4, negative 5, and 3. So this is going to be a scalar multiplication. So we have half times 6, so half of 6 is 3, but it's negative, so it's going to be negative 3. Half of 4 is 2, and then a negative times the negative is a positive, so positive 2. Half of 5 is going to stay as a fraction, and then negative times the negative is positive. And then 3 times half is 3 over 2, and a positive times a negative is a negative. And that's going to be our inverse matrix. And the way that we would verify it or check it is, again, applying what I mentioned earlier. If you get the first matrix, or the original one, and you multiply that by the inverse, it should give you the identity matrix. If it doesn't, then something went wrong. So to multiply matrices, remember it's the first one times the first one. So 3 times -3 is -9. Plus let's just put square. The second one times the second one. So 4 times 5 is 20. 20 divided by 2 is 10. Then we do the second one. So 3 times 2 is 6, plus 4 times -3/2, which is the same as 4 times -3, which is -12, over 2, which is the same as -6. Then we're going to do the second row. So we have 5 times -3, which is -15. Then we have 6 times 5, which is 30, divided by 2, which is 15. Then we have 5 times 2, which is 10. And then 6 times -3, which is -18, divided by 2, which is -9. So plus -9. So then when I simplify this, -9 plus 10 is 1. 6 plus -6 is 0. -15 plus 15 is also 0. And then 10 plus -9 is +1. And that's an identity matrix. So therefore, this answer is correct. Okay, so earlier I mentioned that for inverse matrices, we have the first matrix times the second matrix equals the identity. So using this idea, there's another way of solving for inverse matrices without doing the formula that we just talked about. Instead, you're going to do a system of equations, which is easier on a 3x3 matrix than the formula as well. So I'm going to fill in some variables here so that way we can make sense of this. Okay, so the first matrix times the second matrix equals this. That much we know. Okay, so applying what we know with multiplying matrices, I'm going to set up some equations. Okay, so when we multiply matrices, it's the first times the first. So 3 times A, which gives me 3A. I have the second times the second. So 4 times C is 4C. And that's going to give us our first number in our identity matrix. Then we're going to do the same thing but for the second column. So we have 3 times B. So 3B. And we have 4 times D. So plus 4D. And that's going to give us the second number of our identity matrix. So this equals 0. Then we're going to go to the second column. The second row, sorry. So we have 5 times A. So 5 times A is 5A. Plus 6 times C, which is 6C. And that's going to give us the third number in our matrix. So that equals 0. And then we have 5 times B, which is 5B, plus 6 times D, which gives us 6D. And that's going to give us our fourth number, which is 1. So now we can apply our knowledge of system of equations to solve this. Okay, so I'm going to rewrite it in a different way. We have 3a plus 4c equals 1. And then the other equation with the same variables, which is the third one, 5a plus 6c equals 0. And we're going to solve that system of equations. And then we're going to solve the other one, which is the second equation and the fourth equation, which have the variables b and d. So we have 3b plus 4d equals 0. And we have 5b plus 6d equals 1. And again, we're solving both of them like a system of equations. Okay? So you can either do substitution, in which case you're going to solve for one of the variables and then substitute it into the second equation, or you can do elimination, which is probably the easiest one. So in this case, I want to get a common coefficient. So I'm going to multiply this by 3 and multiply the second one by 2. That way my c's can both be 12, because 3 times 4 is 12 and 2 times 6 is 12. Okay? So 3 times 3a is 9a. 3 times 4c is 12c, and 3 times 1 is 3. And the same thing with the other one. 2 times 5a will give me 10a, and 2 times 6c is going to give me 12c, and then 2 and 0 is still 0. Okay, I want to get these to cancel out, and they're both positive, so I'm going to subtract. So 9a minus 10a is negative a. 12c minus 12c cancels, and 3 minus 0 is 3. Okay, I divide by negative 1, divide by negative 1, so a equals negative 3. So where a is on this matrix up here, we're going to put negative 3, because we know what a is now. Now we need to figure out what c is based on the fact that a equals negative 3. So I'm going to get one of the original equations, let's say the first one, and I'm going to substitute that negative 3. So I have 3 times negative 3 plus 4c equals 1. 3 times negative 3 is negative 9, plus 4c equals 1, plus 9, because I have a negative 9, plus 9, these cancel. So I have 4c equals 10. I divide by 4 because I'm multiplying. So c equals 10 over 4, which can be simplified to 5 over 2. And that, again, that's c, so that's going to be this one, which will go right underneath the negative 3. Okay, now I'm going to solve the second systems. Same idea. So I'm going to multiply this one by 3 and the second one by 2. So now I have 9b plus 12d equals 0. And I have 10b plus 12d equals, equals 2. Sorry. So now I'm going to solve this. So I have 2 positive 12s and I want them to cancel. So I'm going to subtract. So I have 9b minus 10b, which is negative b. These cancel. And then 0 minus 2 is negative 2. So divide by negative 1, divide by negative 1. So therefore b equals positive 2. So where b is, I'm going to put 2. Now, knowing that b equals 2, I have to solve for d. So I have 3b, sorry about that. I have 3 times 2 plus 4d equals 0. 3 times 2 is 6, plus 4d equals 0, minus 6, minus 6. So I have 4d equals negative 6. So now, since I'm multiplying, I'm going to divide by 4. Divide by 4. So d equals negative 6 over 4, which can be simplified to negative 3 over 2. So now, I'm going to go back to the matrix. I put b as 2 already. So now I have to put negative 3 over 2 for d, which is underneath the 2. So if you remember from the way that I did it earlier, this is the exact same answer. The only difference is that we did a bunch of arithmetic to get that answer versus using the inverse matrices formula. Either one works, so it's whichever you're comfortable with.